working on the Herschel mission. Despite anything that NASA might say, it's still the biggest telescope that's ever been launched into space. And I'm still dedicating a little bit of my time to Herschel. This year I've been working with ISO, which is an even older ESA mission. We've been launching a new data archive for the ISO mission, which finished in 1998, believe it or not. But my main interest is Plato, which is a mission that will launch, hand on heart, December the 12th, 2026. We've never had a delay in a launch, so you can put that date in your diary as gospel. And the Plato mission is to look for Earth-like planets around sun-like stars. So anyway, I'm not going to talk about any of those tonight. I am going to talk about the star Betelgeuse. So anyway, let's hit share screen and do that one and that one. Oh, it works. Now, and right, can you see my screen?
Yes.
Somebody says yes. Okay, so supernova Betelgeuse. Okay, I have a great affection for Betelgeuse. It's a star that I've observed myself for many, many years. It doesn't matter where you can live, as it's one of the brightest stars in the sky. You can see it, you can estimate it with the naked eye. I guess I started estimating it back in the 1970s. And I still take my observations of it every clear night. Although, of course, over the last few months, normally I would go out into our communal garden to observe with the binoculars. But with the COVID conditions, theoretically I could do that, but it would be, the restrictions are not quite as tight as they used to be, but it would be not well looked upon. People would not be happy about it. So my variable star observing is limited to what I can see either out of the kitchen window or the bedroom window, and has been since late February. So anyway, Betelgeuse is one star I can actually do out of the kitchen window, which is a distinction at least. So here's Betelgeuse, the photo on the right. Of course, this is a long exposure photograph. It's wrapped in nebulosity. There is a lot of nebulosity around Orion. Alpha Orionis, it's about 10 million years old. I say about. There are a lot of things about Betelgeuse that are not very certain. We know it's a red supergiant star. It's at about 500 to 700 light years distance. I'll say more about that later. It's moderately variable, and it's normally about the 10th brightest star in the sky. So if you can't see Betelgeuse, you can't really see anything at all. So I don't know if anybody in the audience is a monk who's been living on a desert island. Maybe Military Dave, maybe Guy Hurst if he's there. Poor old Guy, I don't think he's been allowed out of the house by Anne for months and months. I don't know if he's online. I gather that Guy is doing a lot better now. Over the last decade, Betelgeuse has been typically about magnitude 0.5. So it's been about the 10th brightest star in the sky. And I can actually remember a couple of years ago, it got really bright. It was as bright as Rigel. And if you were observing it after sunset with the sky still not very dark, having a bright sky background makes a red star like Betelgeuse seem even brighter. And it really was clearly brighter than Rigel in twilight. And that was quite something. Last winter, though, it started to fade, and it continued, and it continued, and it continued. We've never seen anything quite like this, it seems. And all kinds of odd speculation started up as Betelgeuse started to fade. Someone, I don't know who, noticed that two estimates of Betelgeuse's diameter, one taken in 1993, another taken in 2009, showed it had decreased in size by 15%. And so a little light bulb turned on in somebody's mind and said, it's collapsing into a supernova. Now, this is what we know technically as a load of. I'll let you fill in the word there, the dots. Our American friend can probably think of some good ones. They've had some practice for the last 4 years. And even newspapers like the New York Times picked up the story, and the headline, "Just a fainting spell, or is Betelgeuse about to blow?" And the comment in the article, "Astronomers wonder if its explosive finale is imminent." And I was talking to people like Gary Poyner. I guess most of you know Gary. If there is somebody who knows more about variable stars than Gary, I'd like to know who it is. And he was wondering where people were getting all this information from. He was, let's just say, quite skeptical about it, to not put it more strongly. Anyway, things really did get quite interesting, because by the end of the year, Betelgeuse was starting to move into the evening sky, and it was way down below magnitude 1, and everybody was beginning to hear about it. Social media, newspapers, everybody was picking it up. And the question was, just how faint would Betelgeuse get? Now, this had a somewhat less desirable consequence. And it was one that, when I asked Gary about it, he said to me in his broad Brum accent, everybody's going to start observing it now, even people who've never observed a variable star. And that is exactly what happened. Now, the very first observations of Betelgeuse that are in the AVSO database are from 1894, and they're all BAA variable star section estimates. And up until last night, which was when I checked, there were 41,907 estimates, either visual estimates or V-band photometry of Betelgeuse. And that was despite there being a 12-year gap around the First World War, where there is just one solitary observation. In fact, just recently, some observations have been discovered which are going to partially fill in that gap. So around about here, if you can see the cursor, there are several hundred extra observations that have been discovered in astronomers' logbook, and they're gradually being fed into the database. But the remarkable things are, of those 41 or nearly 42,000 observations, more than 40% are from the last 20 years. And in tune with Gary's prediction, 10% of all the data for Betelgeuse was taken in just 6 months after people started to notice the fade. And if you look at the light curve, you can see how it goes from sort of normal density of observations to an incredible number of observations as the fade progressed. So we actually have a big problem with Betelgeuse when we're trying to work out its past behavior and what, if anything, it's doing at the moment is typical, because we don't actually know the historical light curve very well. And this is all the AVSO data for Betelgeuse, all 42,000 observations. Now, Betelgeuse is not very variable. A typical year, it only varies about half a magnitude. And the typical dispersion in the estimates that people send in is plus or minus 0.3 magnitude. So it's a lot more than the actual variation. And you can see that from the light curve, you can actually see very little structure. And it looks as if it faded a bit here, brightened a bit there. But for most of the last 50, 60, 70 years, you can really see almost nothing in the light curve. And it's only quite recently that we've got these green points, which are photoelectric photometry, which are a lot more accurate to help define it. But one of the consequences of having a small amplitude and mostly visual data is it's very difficult to work out, even where there are deep minima. So for example, here, you see some points down as faint as magnitude 2. Is that a very deep minimum? Well, at the same time, you've got other people who are estimating close to magnitude 0. I'll go into this one a bit more now. So what some people have done, and these plots got widely circulated on the internet and on social media, is to take 10-day means. So average all the data in each 10-day interval and see exactly what the trends in the data are. And this is a well-known plot that was produced like that. And you can see when you average the data, the scatter's a lot less, and you can begin to see some kind of structure up and down. Looks to be a really faint minimum there, for example, which is in the 1940s. And you begin to get an idea of its variations, but you can see Betelgeuse is not very bright, sorry, not very variable at all. Late 1920s seem to brighten up, then fade down again over the years. However, there's a problem, and that is the data is so dispersed that depending on actually how you select the start of each 10-day average, you change the light curve completely. And this is an alternative presentation of it. Somebody did a different set of 10-day means. And so, for example, this nice deep minimum here has completely disappeared in the light curve. So the 1946 minimum, there's still something there, but it's not obvious. But the 10-day means you see a deeper minimum in 1947. So what the hell's going on there? And this is the answer. So what I've done is I took the data for those 2 years and just expanded them. And it turns out that that wonderful deep minimum in the light curve depended on just 2 observations from one observer who observed Betelgeuse in late July, very, very low down. And those estimates are of extremely dubious reliability, I would have thought. Then in 1947, a similar problem. You've got an observer who's observing some very faint magnitudes, magnitude 1.8, 1.6 here. But all the very faint observations are a single observer, and at the same time, there are other observers estimating a magnitude or more brighter. So again, I am very, very skeptical of those 2 deep minima. They may have happened, they may not. Certainly in 1947, 2 nights after the estimate that it was down as low as magnitude 1.5, another observer was estimating magnitude 0.3. The data's just not reliable. So can we say that Betelgeuse's minimum has been unique? The minimum it showed earlier this year. All we can say actually is it's uniquely well observed. The data's just not good enough to say whether or not there's been anything similar in the last century. Probably not, but it's not actually clear. So before we go on, let's have a look at what Betelgeuse is and what we can expect from Betelgeuse. Now, it is really a quite special star. However, we don't quite know how special. We know it's extremely large, and we know it's relatively nearby. But we can't actually say that it's the nearest star that could become a supernova, because Antares is about the same size, it's about the same distance, and it's not actually obvious whether Betelgeuse or Antares is the closer or the bigger. So Antares might actually dispute the suggestion that Betelgeuse is the nearest possible supernova. However, we do know that Betelgeuse is very, very big. Historically, people have estimated masses that go from 6 to 30 times the mass of the sun. You know, it's a lot bigger than our sun. The best guess is probably in the range 10 to 20 times the mass of our sun. And it's also big in another sense. It's one of the very few stars that people can resolve with a telescope from the Earth's surface or from orbit. There's just one star in the sky, apart from the sun, before somebody says it, that looks bigger than Betelgeuse, and that's R Doradus. And R Doradus only looks bigger because it's actually a lot closer. And you can actually resolve the disk of Betelgeuse with the Hubble Space Telescope. And if you look at this image, the size of the star in this image, it's a lot bigger than Jupiter's orbit. I mean, it's an impressive size. You can also observe it with a technique called speckle interferometry from Earth, where you actually use the bad seeing to break up the image into thousands and thousands of perfect diffraction limited images like this that can be resolved by your telescope. And you can actually see a little bit of structure that looks like a hot plume of gas on the photosphere of the sky. The trouble is that you can only just resolve it. It's very, very difficult to make out any kind of detail. Now, to know exactly how big Betelgeuse is, we need to know how far it is. Now, if you are like me, I had my Observer's Book of Astronomy. It was the second astronomy book I was ever given. I was 8 years old at the time, and for me, it became the Bible. If Patrick Moore said it in the Observer's Book of Astronomy, it had to be true. Military Dave is laughing. I've still got a copy of it. I managed to find it again. I lost my original copy years ago in my many moves. And Patrick said 520 light years. Now, actually looking at the data, I have no idea where he got that number from. Because there are all kinds of estimates you can find for the distance of Betelgeuse. It's just a bit too far away to measure parallax very easily. So there are two estimates from parallax. One says 650 light years, but with such a huge error bar that it actually goes way off my computer screen. There's another one that says 330 light years, but with the range that goes anywhere from 150 up to 500. The Hipparcos satellite of ESA produced two values. One was 430. Then they realized that they got their numbers wrong, and they calculated again, and they came up with 520 years. 520 light years. But this was years after the Observer's Book of Astronomy that I had was written. So maybe just coincidence, but and then we've got two recent measurements, one from the VLA, the Very Large Array in New Mexico, which estimates 640 light years, and then E. Merlin, so the array of telescopes around Jodrell Bank plus ALMA in Chile, and that comes up with a slightly larger value of 720. So when you put all those together, actually, you've got such a huge range of values. They all disagree with each other that you can only say something between about 400 and 700 light years, not much more. So what about the Gaia satellite? And that's ESA's flagship mission at the moment. It's just produced its third catalogue of stars, 2 billion stars. Not bad. It's a fairly impressive number. Unfortunately, its detectors saturate at about magnitude 6. So it can't observe anything brighter than magnitude 6. Now, if Betelgeuse were 20th magnitude, there'd be no problem. They'd be licking their lips and getting very excited about it. But Betelgeuse is actually very difficult to observe for Gaia. They've got a special technique that they can use to measure stars of brightest magnitude 3, which is difficult. But even at its very, very faintest, Betelgeuse is way above what Gaia can measure comfortably. Now, they have actually observed Betelgeuse a few times, but using a special technique. It's non-standard data. It's going to be very, very complex to reduce. It would be a perfect project for a 6-month trainee, an intern at ESA. That's what they've actually told me, that 6-month stay at ESA, an intern could probably get this data reduced. So I asked the Gaia project scientist about Betelgeuse last week. I guess that he must get asked about it several times each day, because he just said, be patient. It's not going to be in our next data release. I think the very earliest we might see any Betelgeuse data from Gaia is 2025, if we're lucky. So let's assume that Betelgeuse is about 600 light years away. So if you assume that, the ALMA observations, their far infrared image combined with their parallax says Betelgeuse is about 1,400 times the diameter of the sun. It's pretty damn big, 6.5 astronomical units in diameter. So the orbit of Jupiter would fit nicely inside Betelgeuse, and Saturn, Titan would be toasty warm outside. You know, it would be, Titan would be very nice, just like primitive Earth. In fact, there's a lot of speculation that when the sun turns into a red giant, Titan might suddenly become the garden spot of the solar system. One thing to be careful with, though, is that different telescopes give different diameters for Betelgeuse. And generally, the longer the wavelength you look at, the bigger Betelgeuse appears. ALMA observes right out into the very far infrared, almost radio waves. So it's normal that it produces a rather bigger diameter than some other telescopes. Now, if you want to calculate how massive Betelgeuse is, you've got a problem, because we can only say that its distance somewhere in the range 350 to 850 light years is the extreme. Probably it's between about 500 and 700, but the uncertainty is about a factor of 10 in luminosity, which is pretty impressive. Now, you notice a factor of 10 in luminosity. So it's not terribly surprising that estimates of the mass disagree so much. Now, there's actually one very useful test that we've got for ideas of Betelgeuse. It's this little star in the Large Magellanic Clouds, Sanduleak minus 69 degrees 202. Better known to most of you, I guess, as supernova 1987A, because this is the star. You can actually see it in a previous photograph that suddenly exploded and turned into that. Now, I can remember the absolutely disconcerted reaction of astronomers when they looked at the old images of this star, Sandulik minus 69202, and discovered that it wasn't a red supergiant as they were expecting. It was a blue supergiant. And for some time, people just could not understand what was happening. In fact, there were people even saying, maybe we've made a mistake with the star, and they checked and they checked. And finally, it was absolutely certain it had to be this star. It had to be a blue supergiant. And so they started wondering if their models of stellar evolution were even right. And it turns out that actually it gives us a useful test for Betelgeuse, because after looking at the data a lot more carefully, they realized that if a star is as big as Sandulik minus 69202 was, then it's so massive, it's so luminous that it blows off its outer layers and just exposes the hot part of the star deep down inside. So actually, it's having us on. It is genuinely a red supergiant, but it's a red supergiant that's lost all this red luminous cloud outside. And it's pretending to be a blue supergiant instead. So we know that Betelgeuse can't be more than 40 solar masses, because this would have happened. So the fact that the estimates go from about 6 to about 30, that's consistent with what we know from the evolution of very massive stars. It must be less than about 40. Fine. Now, at the other extreme, we can't actually be certain that Betelgeuse will even become a supernova, because to become a proper dyed-in-the-wool supernova, it's got to be more than 10.4 solar masses. Now, the lower mass estimates for Betelgeuse are actually smaller than this. What would happen if Betelgeuse really is genuinely smaller than 10.4 solar masses? It's still quite impressive size. But it turns out that to become a supernova, Betelgeuse must be big enough to become an 8-layer onion. What this means effectively is that you've got to have stable silicon burning in the core of the star. Now, to do that, the temperature has to reach 2.7 million degrees. That's a fairly impressive number. Now, smaller stars can have little flashes of silicon burning, but they can't start stable silicon burning. So that is a sort of limit for Betelgeuse. If it's smaller than 10.4, it's not going to become a proper supernova. In fact, you've got a list of masses and possible fates for Betelgeuse. Less than 7 solar masses, it would only turn into a white dwarf. There would be no supernova at all. Now, that's right at the lower edge of the mass estimates, but it's not quite impossible that Betelgeuse would not be a supernova at all. If it's from 7 to 9 solar masses, yes, it would become a neutron star, because it would collapse to a degree, the protons and the electrons would combine, and it would produce what is called an electron capture supernova, which is a low luminosity supernova, a sort of failed supernova. Now, more than 9 solar masses, then you can have a little bit of silicon burning. You can have a silicon flash. You can have what they call silicon deflagration. So when the star starts to collapse, the silicon all burns suddenly. again, it would be a low luminosity supernova. It wouldn't be a proper supernova. It's only if you get above this limit of 10.4 that you get a proper core collapse and a proper supernova. Right-hand side, just to give you an idea of how uncertain some of these things are, this is two indications of the comparative size of certain stars. Some measures say that Antares is much bigger than Betelgeuse. Other groups put it the other way around. Betelgeuse much bigger than Antares. Same thing with Aldebaran. Compare Aldebaran and Rigel. Some groups estimate that Aldebaran is bigger than Rigel, some the other way around. It's all down to the difficulty in estimating mass, knowing the distances of stars. A lot of the Aldebaran is one of the stars that actually we do know its distance well. But Rigel, Antares, Betelgeuse, they're all too bright to observe well with a satellite like Gaia and too distant to measure parallax from the Earth. So we've got a sort of Sudoku with the mass of Betelgeuse. Now there are three groups that have tried to solve this Sudoku and work out the actual mass of Betelgeuse. And they've come up with three completely different numbers for the solution. One group came up with 9.5 solar masses, one came up with 11.6, one came up with 19.5. So real agreement there. You know, it's like the agreement in the vote count in Pennsylvania, for example. You know, one guy says that he won by tens of thousands of votes, and the other guy says actually he won by hundreds of thousands of votes. You know, it's not that I'm saying that Donald Trump actually is any better at arithmetic than your average 6-year-old kid. Well, most 6-year-old kids, I think, are better at arithmetic, but maybe our Georgian from Florida would disagree. So if the lower mass estimate is right, you get a supernova fail. Something would happen, but it wouldn't be very spectacular. Now, how did they get these estimates? Well, there are two basic methods. Both sets of methods claim that they are absolutely reliable, which is why they disagree completely. One method is evolutionary models. So you say, okay, Betelgeuse started as a main sequence star. It's evolved off the main sequence. It's expanded into a red giant. It's lost a little bit of mass because it's pulsating. It's blowing off mass into interstellar space. And you try and calculate how big it must be for the path it's got on the Hertzsprung-Russell diagram. And they come up with 19.5 solar masses with a very small uncertainty between 19 and 23. So they're very confident in that estimate. Then you can use the Hubble Space Telescope and you can measure the surface gravity of Betelgeuse from the width of its spectral lines. That comes up with quite a wide range of values, a very wide range. 7.7 up to 16.6, but the most likely value is about 11.6. And then you have an estimate from interferometry measuring limb darkening, and that comes up with 9.5. And really, it's very hard to see how you can get an agreement between the three methods. You'd say that these two, well, they're more or less in the same ballpark, but they disagree by a factor of 2 from the evolutionary model. There's something horribly wrong somewhere, and nobody knows what it is. So the conclusion is that Betelgeuse is either one of the most massive stars known and almost big enough that when it explodes, it would produce a black hole, or It's possibly not even big enough to become a proper supernova. Completely contradictory results. It's great. So let's imagine that Betelgeuse does become a supernova. What would happen? Now, most people seem to assume tacitly that Betelgeuse is about 20 times the mass of the sun. Maybe that's wishful thinking because you get a bigger and better bang that way. Is Betelgeuse already an 8-layer onion? Is it already burning silicon? Almost certainly not. But if it is, get in down to your shop and buy your sunglasses, because it means it's going to blow in the next 24 hours. What do I mean by that? Well, it turns out that red supergiants like Betelgeuse, when they get to the end of their life, really are in a hurry. If Betelgeuse is 20 solar masses, hydrogen burning will last 8–10 million years. Helium burning will last 500–600,000 years. Carbon burning will last about 1,000 years. But then the next stage, when you get down to oxygen burning, that's only going to last about 6 months. Neon burning lasts about a week, and silicon burning is only going to keep Betelgeuse going for about 1 day. So the last few stages of Betelgeuse's life, its evolution, are incredibly rapid. So the guess that most people have got is Betelgeuse is about 80–90% through its hydrogen burning phase. We're probably about 100,000 years from a supernova. So we're also getting towards the end of helium burning, but we're not yet burning carbon in the center of Betelgeuse. What if we're wrong? What if Betelgeuse is already burning oxygen? What would happen? Well, the switch off at the end would be extremely fast. We would go through the last few phases of in a very short period of time. And then when the nucleus of iron from silicon burning builds up, suddenly the core becomes large enough, the core of iron becomes large enough that it can't generate enough heat, enough energy to keep the star inflated. And all those 20 solar masses collapse down on the star. That core collapse would take less than 2 seconds. Some estimates say as little as 1/4 of a second. The first news of this would be not the 23 neutrinos that we saw from supernova 1987A. The first news we would get that Betelgeuse is blowing is a burst of about 1 to 2 million neutrinos. Every single neutrino detector on Earth would blow a fuse, literally. They would be overwhelmed. Now, this would come something like 20 hours before the visible light of the explosion reaches us. So people would have plenty of warning. You would know the day beforehand to get out your sunglasses or your Barda filter and have a look at Betelgeuse the following night. Now, if you scale from the Crab supernova, you'd expect Betelgeuse to reach about -10 magnitude. It would be as bright as about a half moon. Some estimates put the peak brightness as high as magnitude -13. It would become a real problem for astronomy because it would be like having a second full moon in the sky, but concentrated in a single tiny point of light. Now, all I can say is that 2 nights ago, Betelgeuse was still there because I looked out of the kitchen window, got my mobile phone, This is a 1/8 of a second exposure with my mobile phone. And you can see Betelgeuse is still there. It's fainter than it was a few months ago. It's about magnitude 0.8 at the moment. It's clearly fainter than Rigel. One of the things that impresses me about this photographing, there was some clouds, so the conditions weren't that great. You can see the Orion Nebula there. On a decent night when it's clear and transparent, I can see 4th magnitude stars clearly in a 1/8 of a second exposure with my mobile. So I think supernova Betelgeuse shouldn't be a problem for me. So back to the original question. Is what we're seeing evidence that something terrible is about to happen with Betelgeuse? And what people know is that over the last 5 years, it's been going up and down increasingly violently. And that's one of the reasons why people start speculating. Maybe this is the prelude to a supernova. But it turns out that we've got a light curve of Sandulik minus 69,202 for a century before it went supernova. So we've seen it through the end of carbon burning, oxygen burning, neon burning, silicon burning, and nothing actually strange happened in the light curve. Even the night before, the images that we have of that star are perfectly normal. So these increasing variations in Betelgeuse, whatever they are, don't seem to be evidence of an imminent supernova. We can also get a little bit of information about Betelgeuse's behavior in the past. Now, Ptolemy and Bayer both describe Betelgeuse. This is Bayer's catalogue of the stars. And for Orion, Betelgeuse, it says, I assume that you all read Latin perfectly, but what it says here, in humero sinistro lucida rubescens Betelgeuse aratus gloea bocat. So basically it says in the left shoulder of the giant, the red shining Betelgeuse. And he just says luminous primi, 1st magnitude. And he puts it at the same level as Rigel. People have speculated that maybe Betelgeuse was particularly bright that year, but it looks as if he actually just copied the description of Ptolemy, because Ptolemy also described Betelgeuse as red and 1st magnitude. No more, no less. Now, we know Sir John Herschel discovered the variability of Betelgeuse in 1836. And one of the reasons why he noticed it was that the following year, Betelgeuse got exceptionally bright. Both in 1837, 1839, it got up to negative magnitude, clearly brighter than Rigel. And 1852, it was negative magnitude again. So it has in the past got really quite bright. The 20th century, though, most of the time, it's varied between magnitude 0.5 and 1. Very little variation. Now, people have looked at this APSO light curve, and they've suggested that maybe there's a 5-year period in it, although nobody's got any particular faith in it whatsoever. There was an analysis of the light curve in the 1980s that found all kinds of periods. None of them particularly convincing. 20 years, a couple of periods around 6 years, one around 9 years, one around a year. Nothing very convincing there. The light curve is such a mess. It's very difficult to get anything. However, the last 10 years, if we've seen something really odd is going on. Betelgeuse has gone from being almost non-variable to these increasingly large oscillations, which over the last few years really do look quite periodic. And each cycle has got bigger than the last one. In fact, the entire known light curve range, magnitude +1 to +1.7, has occurred in the last 3 years. And it also looks as if over the last 5 years, Betelgeuse has got systematically a bit fainter. So maybe something odd is going on with the star. Now, people have got very excited about this period in the star, and it's been calculated as being about 430 plus or minus 10 days. Buyer beware. This very impressive period in the light curve is only obvious for the last 5 years. In fact, people have analyzed photometric photometry of Betelgeuse, the most accurate photometry over more than 20 years now, and they only see this 14-month period in the last 5 years of data. It's dubious. It is very, for me, when you see something suddenly appear like that, a period, the most likely thing is it's suddenly going to disappear again, just when you start to believe it. So believing this 430-day period, as I clearly do, implicitly, one explanation of what happened last year is that the 430-day period and the 6-year periods just coincided. So both showed a minimum this year, and that's why we saw a particularly deep minimum. And it means that 3 years ago, their maximum would have coincided. Fine, we saw a very bright maximum. However, more than 3 years back, this cycle just completely disappears. There is no evidence at all of previous supermaxima and minima. And the combined amplitude of the two periods is far too small to explain the variations that we're seeing anyway. So I don't believe a word of it. And I think Gary believes it even less. But there are people who are still keenly promoting this idea. We will see. Another way of trying to work out what is going on in Betelgeuse is to look at the spectrum, the light of Betelgeuse, the fingerprint of the star. Now, because Betelgeuse is a red star and it's cool, we know it shows very strong titanium oxide lines. It's one of the few molecules that's strong enough to form in the atmosphere of stars like this. And there's a sequence that the cooler the star, the deeper these lines go. You can see this star, HE 94096, relatively warm. The line's not very deep. 100 Kelvin cooler, and the line has become much stronger. Now, there are spectra of Betelgeuse that followed it through the minimum, and they say, or they show, that in just 4 months, Betelgeuse cooled by nearly 100 degrees centigrade. The titanium oxide lines got much stronger, but photometry at 1 micron, so where you have no titanium oxide lines, showed the variations, or there was hardly any variation at all. The star didn't fade at all. Now, this is puzzling because we know that Betelgeuse is a pulsating star like Cepheids, and pulsating stars get fainter when they're larger and cooler. There's a cycle. A star like Betelgeuse, you'd expect it when it's biggest and coolest to be faint, and when it shrinks and gets a little bit warmer, it would be brighter. However, the photometry that we've got for Betelgeuse show that it actually got 8% smaller as it cooled and faded, which is not playing by the rules. It is completely the opposite to what you'd expect. So something is wrong somewhere. And the problem is Betelgeuse itself. Now, these are two observations with the very large telescope, the 8-meter telescope in La Silla in Chile. Now, the calculations that were made of the size of Betelgeuse from its temperature, its brightness, depended on Betelgeuse remaining spherical and symmetrical. January 2019, well, more or less. December 2020, sorry, December 2019, as it was fading, I've got half my screen covered by the participants, so I can't actually see the right-hand side of the slide. It doesn't look even approximately spherical. There's a dark patch here. There's a brighter patch up there. Something is happening to the star. And the reason why the calculations, the temperature, the diameter, don't give the right answer is that it is no longer spherically symmetrical. So what is that big dark patch? Now, some people suggested that it was a cloud of large dust grains, that they blocked the visible light, but they let the longer wavelength infrared light come through. And that's why Betelgeuse didn't seem to fade very much in the infrared. However, there are other observations that further into the infrared that suggest that Betelgeuse didn't fade at all during the great minimum that we observe visually. And they suggest that the observations are actually more consistent with giant star spots. So what we're seeing here is actually a gigantic star spot on the surface of Betelgeuse. So one possibility is that this 430-day period, the 14-month period that people are observing recently, is just the sunspot cycle of Betelgeuse. Is that possible? Probably not, because we know the rotation period of Betelgeuse is about 36 years. So it seems very unlikely that the sunspot cycle is only a tiny fraction of the rotation period of the star. It's much more likely to be some period of pulsation. But the fact the rotation is so slow means that when a huge star spot forms, it will stay visible until it's decayed away. It won't rotate off the disk. So what would we expect to happen this winter if Betelgeuse really has only a 430-day period? Well, the prediction was that it would reach maximum brightness somewhere between magnitude 0 and 0.3 in August and September. And then it would drop down again to minimum brightness in April next year. Fine. What actually happened? Well, it turned out that this summer, by a lucky coincidence, someone persuaded a NASA solar satellite to observe Betelgeuse whilst it was at solar conjunction. And it turned out that it observed Betelgeuse fading, and that when Betelgeuse came out of solar conjunction, it was already almost magnitude 1, almost as faint as the predictions were for next year's deep maximum. So something has clearly been going on. So NASA's Stereo satellite observed Betelgeuse on June 24th, July 13th, and July 20th. And it registered a steady fade during this time. So it was actually able to fill in the gap in the light curve when visual observers couldn't observe Betelgeuse. And you can see a really quite impressive fade. Here, when the prediction was that it should have been at maximum light, it most definitely wasn't. Now, how did stereo do that? It's because there are two stereo satellites, stereo E and stereo B. One is 60 degrees ahead and the other is 60 degrees behind the Earth's orbit. So they actually see round the edge of the sun. Stereo B failed several years ago, but stereo E still works. And even it's used normally for observing the far side of the sun, but it can actually roll away and observe star fields, and it can observe down to about magnitude 12 and actually get quite reliable photometry. So we were very lucky. The engineers, the scientists were persuaded to point it away. It gave us some information about what was going on in this gap when normally you would not see Betelgeuse. Now, I've continued observing it, as have many other people, and my magnitude estimates since conjunction around about magnitude 0.6. I've been seeing it a little bit fainter recently, but they're fairly consistent with everybody else. We'd expect the big fade to start sometime around the new year. So let's do something a little bit ambitious. We've got the light curve from 2020, what was seen up till October. We've also got the light curve, what was seen last year. And last year's light curve, actually, this part really does look quite remarkably like what we've been seeing so far since conjunction. If you suppose that what we observed in August last year will repeat in October this year, you would get a sort of prediction of what Betelgeuse might do over the next few months. So let's just stitch those two light curves together. Yeah, this is a stitch up, Dave. It's a stitch up. Move the light curve forward 430 days, and this is what you would predict. You would predict Betelgeuse to get a little bit brighter through into November, then fade again, and then really drop off the edge of a cliff around about the end of December. What has actually happened? Well, actually, we've now got more data since I made this rather optimistic model. And actually, you can see that the structure we're seeing, there's a little brightening, then it starts to fade a little bit. It actually does look remarkably like what people were seeing last year, actually a little bit advanced from what was seen last year. So I'm just wondering if sometime in the next couple of weeks, Betelgeuse is going to start fading rapidly. I'm very skeptical about it. Anyway, the conclusions that I would have about Betelgeuse: no, it's not about to go supernova. Do not believe Donald Trump. Do not believe the New York Times. We're not even sure it will become a core collapse supernova. That remains to be seen. It may not even be the closest supernova candidate to Earth. Maybe that Antares becomes a supernova first. The 2020 minimum was probably due to massive star spot activity. But if Betelgeuse produces another massive star spot exactly 430 days later, next year, I'd start to become a little bit dubious about that theory. Sunspots do not behave regularly like that. Other experts are saying it's due to dust ejection. Now, dust ejection, if Betelgeuse is pulsating, you can think how you might get clouds of gas in a fairly regular sequence, maybe. And they partially a cloud of dust like that would partially block the light of the star. So if that period is valid, we'd expect a minimum to around magnitude 1 around April the 8th, 2021. So just as Betelgeuse is beginning to disappear into conjunction again. However, what we've seen over the last few months shows that a lot more things are going on than a single dominant light curve period. So all bets are off. If my predicted light curve is right, I will be very pleased, but I will also be absolutely staggered, because I would be amazed if this periodicity held. So my final conclusion would be, yes, Betelgeuse is a fascinating star. So thank you for watching. Thank you for listening. If anybody's still awake out there, it's time for questions.